Thank you, Mr. Chairman, for the introduction. My name is Ilhan Özgen, and I come from Berlin, and I'm currently a fellow of the research group Urban Water Interfaces, which is funded by the German Research Foundation. So the topic of my talk is integral porosity shallow water models, which are a specific type of free surface shallow water models, and that are derived to reduce computational time for urban flood forecasting. And they do this by enabling simulations on coarser grids, basically. I'm also a visiting scientist right now here in Kobe, and I came in January together with my wife, and this is my first time in Japan. And so during the end of January, my wife decided that she wanted to visit Okinawa. So she flew to Okinawa and enjoyed the warm weather there. And I stayed here and worked. But so on January 23rd, I was surfing the internet when they said that there was an earthquake of magnitude 7.9 on the Gulf of Alaska. And so I don't know very much about tsunami, but I know that they are generated by earthquakes. So I was a little bit worried, and I searched if there is a probability, a risk of a tsunami affecting Japan. So I searched, and I found that they have issued a tsunami warning for the west coast of Alaska and also for Hawaii. And so I thought, if that is Hawaii, then also probably Naha will be also affected, and I was a little bit stressed. Fortunately, the warning was lifted. There was not tsunami generated by this earthquake. But I think this kind of situations highlight the importance of fast forecasting tools that we need. So the wave approximately needed 4 hours to reach Hawaii. And so it is essential to know if a place should be evacuated or not. And these are time-critical applications, which means the results should be available very fast, so we know which place to evacuate. Usually for flood forecasting, shallow water type of models have been used. So these are solving the depth average two-dimensional shallow water equations in the urban area, and then you get predictions for water depth and velocities. So the water depth is, of course, the primary target here to design preemptive measures and support decision making. And usually there is the model part of it, which is the governing, the mathematical aspect of it, and then there is input data, which is the geometry of the urban area and topography information. So the building information and topography information. And then you combine, or you input the data in your model and you run the simulation, and then you get your results. And this runtime is very crucial, so as you all know. There are certain techniques which help to accelerate the process, and one is high performance computing, and the other one is adaptive methods. And what I will talk about today is so-called scaling methods, which the name implies that we move from a smaller scale to a larger scale by applying some kind of averaging techniques. And this is achieved in my particular case by using porosity parameters. And the idea is actually quite simple, and it is borrowed from the groundwater modeling from the soil sciences. So the problem is that the phenomena of urban flooding is a multi-scale phenomena. So that means that we want to simulate or get results for a rather large domain, but processes at a much smaller scale influence the global behavior of the simulation or of the phenomena. So this is also true for groundwater modeling, because soil is very heterogeneous, and it has macropores and impermeable small singularities inside of it. And so in soil sciences, they use something that is called a homogenization, which means they will take the heterogeneous soil and somehow derive some average parameters from it, which they express also as a porosity. And so the idea is, can we apply this? Can we view a building block in the urban area as a porous medium? Because if we can, then we can not discretize explicitly the buildings as is shown on the right side, but we can coarsen the size of our computational cell. So so I have tried to sketch the ideas. Usually this mesh is also considered coarse because to accurately capture hydrodynamics, it is suggested to use 10 cells between buildings. But to give you the general idea, usually one would try to very accurately, one would use very small cells to capture the effect of these buildings, and then you would impose a larger bed elevation at the cells that are located inside the buildings, and if we can derive some porosity parameters from this configuration, we can use a much larger computational cell where the buildings are not explicitly represented anymore, but are taken into account by using these porosity parameters. So this is the essential idea of these models. And the governing equations are pretty much similar to the conventional depth average shallow water model. So we have the vector of conserved variables, the time derivative, and the fluxes of it in the spatial derivatives, and then of course the source term. And so in vector form, these are written like this. So would be the water depth, and the unit discharges in x and y direction. And the flux vectors are then functions of these conserved variables. So what you essentially have is the momentum balance and the mass balance in 2D. So all of these quantities are depth averaged. This is the conventional shallow water model, and we can introduce porosity by simply, sorry. So this is the source term. This would be the bottom slope source term, and this is the friction source term, which I have written for sake of completeness. So, okay, this is the classical shallow water model, and if we want to introduce porosity, then we can just so for the integral porosity model, we need the integral form of these equations, which can be achieved by integrating over a control volume and then applying the Green-Gauss theorem. Then the equations become of this form. So you have an integral over the domain, and the flux, the integral of the divergence of the flux is transformed into a line integral over the boundary of the control volume. And so now finally I think I come to my slides. So if I want to introduce porosity, we do this by firstly introducing something that is called a phase function, which is theoretically evaluated at each point inside the computational cell. So and it is a binary function which returns 0 or 1. So 0 if the point is coincides with a building, and it returns 1 if it lies outside of it. So for example, this point evaluated at this, the function evaluated at this point would return 0, and the function evaluated at this specific point would return 1 because it does not coincide with the building. And we multiply all the terms of the conventional shallow water equations with this phase function, and we define the porosity terms as the integral of the phase function divided by the total area of the cell. So this is the mathematical formulation, but what it actually means is that the porosity represents basically the fraction of the cell which is available to the flow. And if I integrate it over the edge, I get a conveyance porosity, and this one represents the fraction of the edge which is available to flow. And as a result, I get several porosity parameters which are directly derived from the underlying urban geometry. So storage porosity, again, it is the fraction of the cell which is available to the flow. So the blue area divided by the total area. And all of these conveyance porosities, 1, 2, 3, and 4, they represent the length of the edge that is available to the flow. And then I can very simply solve this by using a finite volume formulation. I just have to find a method to calculate the numerical flux. So it is very much similar to the conventional shallow water model, but it differs in some aspects, and these are actually it differs in the source term, because we had these two terms inside the source term of the conventional shallow water model, which was the bed slope source term and the friction source term. And because we now move to a larger scale, we have two additional source terms, which are the stationary pressure term that is acting between the solid and the fluid, and we have a building drag dissipation source term. So the first one is a stationary source term, and the other one is a dynamic source term. And I will now explain these source terms a little bit more. So this is the interface pressure source term. It is the pressure that acts at the interface between the building and the fluid. And because we use now this cell, so we are now looking at the urban domain at this resolution, we cannot resolve this interface anymore. So we have to, so it comes into the source term, basically. And it is a stationary source term because it does not depend on the velocity of the flow, it is always there. So because we cannot resolve this interface, what one does in the model is that we shift this influence to the edge of the cell, and we express it as the hydrostatic pressure, evaluated for a constant water elevation inside the cell. And the second source term is the drag dissipation source term, which comes from the interaction of the flow that hits the building. And this one is expressed as a drag force formulation. So here this one would be the friction source term, which is the same as in the conventional shallow water model, but this one is the drag coefficient. So you get an additional source that dissipates the momentum, and it depends, as I mentioned before, so it depends on the velocity of the flow. So it is a dynamic source term, and it disappears if there is no velocity. You don't have the drag dissipation source term. So these are the two specific source terms that are related to these porosity models, and I will now just demonstrate the performance of this model by showing you a test case that features a flash flood through a idealized city. The city does not exist in real. And the setup is as follows. Now, this is the discharge that has been measured at the outlet of a natural catchment after an intense rainfall. And so we simulated this discharge, and we impose it now as a boundary condition to a rather idealized city model. So these holes inside the computational mesh represent the buildings, and the curve, the hydrograph I showed before, is the inflow boundary. So the scenario would be that this city is located at the bottom of a mountain, and heavy rainfall occurred, fell onto the mountain, and this would cause a flash flood inside the city. So at this side you see the high resolution model, which I used to get the reference solution, and at this side is the coarse model, so this is the porosity model. And there are 3 measurement points here at 3, 2, and 1. And we are interested, or we will compare results at these gauges. We will see how the water depth evolves. And I will give you the benefit of using coarser grids now. It's so the high resolution model uses about 8,000 cells, and the porosity model uses about 700 cells. So it is much lesser cells, which means it is much more cheaper to compute. These are some snapshots during the simulation. So this is 600 seconds in the simulation time, and so we can see that the results agree quite well. The propagation of the wave has been captured quite well. And as the simulation progresses, we see that the results still agree. And now, comparing the gauges, we see that so the black line would be the reference solution, which we try to approximate with our porosity model, and the red line is the porosity model. So you see that the agreement is quite okay. So the peaks, the arrival time of the peaks, and the overall quantity of the maximum water depth is captured fairly accurate at these 2 gauges. And here there are some deviation between these 2 curves. And when I look at the locations of these 2 gauges, so the third one is located just in front of the building block. So this one shows good agreement. This one shows a little bit deviation. And this means as the flow progresses through this domain, due to the porosity, or basically due to the way we consider the buildings, an error is introduced into the model result. So gauge 1 is the most far away gauge, and there are significant deviations between the water depths. But overall, a very good agreement has been achieved, and CPU time reduces about factor 100. And of course, the main reason for this is because we use bigger cells, or less. The cell number has been reduced, so the computational time reduces.